Okay, let's take a look at a rational function where the numerator is 1 degree higher than the denominator. So we're going to look at the template f of x is equal to axn plus 1 plus c over bxn plus d. Now, in this scenario, you need to remember a few things here. There actually won't be a horizontal asymptote, so it won't exist. Right? Vertical asymptotes will still exist. It's basically when the denominator is equal to 0, right? So basically the restriction is when the denominator will become 0. And we also have something called an oblique asymptote. Now you might also hear of this as a slant asymptote, right? And I'm going to consider all of these things when I show you guys how to sketch this. Now, specifically, if we want to find an oblique asymptote, this only occurs when the degree of the numerator is 1 higher than the denominator. What we need to do here is we need to, if we have a function, right, the numerator is n of x and the denominator is d of x, right, if we divide these two, right, if you do n of x divided by d of x, we'll get some kind of expression, q of x, plus some kind of remainder. Now, the oblique asymptote actually occurs when y is equal to q of x. Okay, so this is basically the oblique asymptote, right? And it's going to be a linear equation because once again you're dividing by a denominator that's 1 degree less. Okay, so I'm going to show you guys this when we do this question now. So let's start with the domain range. I think the best way is through demonstration, right? So the domain here, x belongs to all real numbers, but x cannot equal -3 because basically if we have f of -3, we're going to get some kind of constant c over 0. So this indicates that we have a restriction, and this also demonstrates a vertical asymptote. Let's take a look at the range here. We can say y belongs to all real numbers, but y, in this case, because there is no horizontal asymptote, we'll keep it at y belongs to all real numbers. There is no restriction on y for the time being. Okay, so once again, we'll keep it at this point. There is no horizontal asymptote, right? So keep that in mind. So the next part here is the asymptotes. We can notice that the vertical asymptote, x is equal to -3. There is no horizontal asymptote, but then the next challenge comes to finding the oblique asymptote. So to find the oblique asymptote, we actually have to do division. We actually have to do long division. Okay, so if I'm doing long division here, and you could do synthetic too, because as long as the divisor is a linear expression, I'm just going to do long division because I think it's easier. So you have 2x squared minus 8, you get x plus 3, and in this case what you want to do, I'm just going to fix that up a little bit. Right? In this case what you want to do is you want to match the leading coefficient. So I'm going to multiply this by 2x, you get 2x squared plus 6x, and then I'm going to subtract it, and then these cancel out, and you get, pretend there's a 0 here, 0 minus 6x, -6x, minus 8, got to match the leading term, which is -6x, and what I'm going to do is multiply by -6, so you get -6x minus 18, and you can stop there because you can notice that the next step here is remainder. You're going to get a remainder of 10, but that's not important. What is important is the quotient, and the quotient is our oblique asymptote. So the oblique asymptote here is y is equal to 2x minus 6. So this is a linear equation, right? And because it's a linear equation, instead of me using rise or run in the y-intercept method, what we could do here is, instead of me using rise or run and the slope-intercept method, what we could do here is we could actually use the intercept method to find the two intercepts and easily graph this function. Okay, so if I wanted to find the intercepts of this oblique asymptote, which is basically a linear function, mx plus b, right? So it's going to be a line. The idea here is that if you're using the intercept method, the y-intercept here is 0 and -6. The x-intercept is basically, if we let y equal 0, 2x minus 6 is equal to 0, 2x is equal to 6, x is equal to 3. So the x-intercept is 3 and 0. Okay, so that is what the x and y-intercept look like for the oblique asymptote. But let's find the x and y-intercept of our original function, right? So if we're trying to find the x-intercept of our function, right, just like other rational functions that we looked at, we just have to let f of x equal 0, which is ultimately we need to set the numerator to equal 0, because the only way to make a fraction 0 is if the numerator is equal to 0, move the negative 8 to the other side, we get 2x squared is equal to 8, we divide by 2 here, x squared is equal to 4, and if we do the square root, we get plus minus 4, so x can be equal to plus minus 2. Okay, so there's going to be two x-intercepts that get generated here. Okay, so one of the x-intercepts is negative 2 and 0, the other x-intercept is positive 2 and 0. Okay, it's negative 2 and 0, and positive 2 and 0 are x-intercepts. Now we also need to find the y-intercept, and let x equal 0. If we do that, we get f of 0 is 2 times 0 squared minus 8, 0 plus 3, so you get negative 8 over 3. Okay, so the y-intercept here is 0 and negative 8 over 3. Okay, so now we have our y-intercept, we have our two x-intercepts, and we have the oblique asymptote. Let's create a sketch. So I'm going to create a graph here really quickly. Okay, so here's my grid. I'm just going to plot some of these points. Let's start with our x and y-intercepts of our original function. So our x-intercept is 2 and 0, and negative 2 and 0. Okay, so here's 2 and 0, negative 2 and 0, and the y-intercept here is 0 and negative 8 over 3. Okay, so it's negative 8 over 3, and 0 and negative 8 over 3, it's like negative 2.67, so let's say it's like somewhere here. Okay, slightly past the middle. So 0 and negative 8 over 3. Okay, we also want to put down our vertical and horizontal asymptote. So the vertical asymptote is negative 3. Now there is no horizontal asymptote, right? So the vertical asymptote is negative 3. Let's say it's like somewhere here. Okay, so this is a vertical asymptote. X is equal to negative 3. Okay, I'm just going to keep going down. Right, guys, use a ruler for this. Right, and beyond that, we also have an oblique asymptote. So the oblique asymptote here is, we have the equation y is equal to 2x minus 6. I'm going to use orange to represent my oblique asymptote. And my oblique asymptote has the intercepts 0 and negative 6. So let's plot them based on the intercepts. 0 and negative 6, as well as 3 and 0 for the x-intercept. Okay, so this is our oblique asymptote, and what we have to do now is we can just kind of combine the two, right? We can just connect the lines. Okay, once again, guys, just use a ruler for this. Right, see, I off-shot it, but I think you guys understand what's going on. Okay, I can't really extend this further, right? And in this case, this is what a graph will look like. Okay, so that's what a graph will look like, and just based on this point, we actually have a point of intersection of the vertical asymptote and the oblique asymptote. Okay, so this point where they intercept, we call this a crossover point. And the crossover point actually occurs, we know that the oblique asymptote is y is equal to 2x minus 6, right? It's 2x minus 6. So the idea here is the crossover point occurs, they have the same common x value, right? So y is equal to 2 times negative 3 minus 6, which is negative 6 minus 6, which is negative 12. So this crossover point actually will occur at negative 3 and negative 12. Okay, so this point definitely won't exist in the function, but it's just where you'd find the two asymptotes intersecting, right? Now using this notion, we can actually sketch a graph. Okay, so when we sketch a graph, and I just showed you one half of it, right? You connect these points, and you can follow the asymptotes to create this sketch. Okay, so that's basically our idea here. So I'm just going to label the x-intercepts out and the y-intercept. But you can notice that it's not really a parabola, and it follows the confines of the asymptotes. Now you also see another sketch somewhere down below, right? But that's really the idea. Okay, and what we could do here is we could analyze some of our end behaviors as well. Okay, so here's another view of the graph on the left, right? So I just kind of used a much more larger scale, so it made the graph actually a bit smaller, right? So each unit was worth 4 instead of 2. And in this case, you can actually notice that the curve here, there's actually another curve between the oblique asymptote and the vertical asymptote below here, and this indicates that we actually can see that there's two of these functions in opposing quadrants. All right, so you want to keep this in mind, and this is going to help us to determine the end behavior. So that's what I'm going to do next. The end behavior here, and I drew this smaller graph, another view of this graph. It's the same graph really. I drew another view of this graph just so you guys can see the end behavior to the left of the asymptote. Okay, so this is the asymptote being approached from -3 from the left side. It's the asymptote -3 from the right side. This was just a enlarged image of that. And if we're looking at as x approaches -infinity, right? As x approaches -infinity, y here is, and as we go basically this way, y here is going all the way to -infinity. Okay, so y is approaching -infinity. As x approaches the vertical asymptote from the left side, y here is approaching, as we go this way, y is approaching, you can notice that it also goes to -infinity. You can follow the blue trace. As x approaches -3 from the right side, so as we're approaching -3 from the right side, like -2.99, if we follow this trace to the very far right, you can see that this goes to positive infinity if we follow the trace in blue, right? And as x approaches positive infinity, right, as we go this way, you can see that the graph y also approaches positive infinity. Okay, now although the range is slightly tricky, you would definitely need calculus as a tool to kind of help you sketch this. Right, you can notice that there is a low point here, but we haven't done any test points, so this isn't the full figure of the graph, right? Although you can imagine that, you know, there's going to be some kind of gap somewhere here, right, of y values, right? For the time being, we will just for simplicity's sake, right, because this is a functions course, we'll just say that the range y belongs to a set of all real numbers, right? We don't need to be very specific with this, but I think by sketching the function out, it'll give us a much better picture of what this function's characteristics look like, right? So yeah, this is the idea. It does get a little bit more complicated as we go on with